Chemical kinetics is the study of rates of reaction. If you were to look at this reaction between iron and oxygen, and you looked at the basic chemistry, Fe plus O2 yields Fe2O3, the equation here describes all three scenarios that you see above. But certainly the rates of these reactions would be very different. You had a large piece of iron that slowly over time began to rust. The reaction rate of that would be quite slow. If you look over here, you've got powdered iron metal thrown into a flame, which provides the activation energy necessary to get this reaction going faster, and you have a much faster rate. Over here, you have a similar rate with the iron reacting with oxygen, but this time we've got a pure oxygen environment. So the higher concentration of oxygen leads us to a higher rate of reaction. All of these have the same basic chemistry, and in fact all have the same spontaneous delta G if you think about your previous chapter. The difference is this little part of the reaction, the activation energy, or E sub A, and the activation energy has changed for all of these reactions due to the states of matter that they are in, or with catalysts provided perhaps, or increasing concentrations of reactants. So activation energy and the rate of a reaction are what our next chapter will deal with. If we look at kinetics, it really is simply the study of the rate of a reaction. So reaction rates are going to proceed by rate laws. And eventually, rate laws are going to allow us to determine a mechanism of a reaction. So eventually, once we pull all of our kinetics together, we'll have an understanding of a rate of a reaction, okay, and a mechanism of that reaction. This is going to take us some time to get through, but eventually we'll have a pretty good understanding of what it is that controls rates of reactions and how we can alter those factors. Let's start with the basics of collision theory. In order to react, molecules have to collide. That makes pretty logical sense. Molecules must collide in order to react. But they must collide with enough energy and the right molecular orientation. So not just the energy, but also the correct molecular orientation or relationship of the molecules to one another. Since only a small number of collisions can actually be effective, okay, because you're not always going to have enough energy and the right molecular orientation, only those effective collisions can actually cause a reaction to occur. So again, you need enough energy to overcome the activation energy barrier, and you need those effective collisions. The collisions must involve enough energy to get over the energy barrier. That means they must have enough energy to equal or exceed the activation energy, and they have to allow orientation of breaking of bonds and forming of new bonds.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2. For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting. If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
So you see that you need both conditions. activation energy is the minimum energy needed to make a reaction happen. We've mentioned this numerous times. What you may not be aware of is that an activated complex will be formed. An activated complex or a transition state will be formed at the top of that energy barrier. So if this is the energy of your reactants, and you need to climb this energy barrier, and assuming this is an exothermic reaction, if you get to the top of this energy barrier, okay, you have formed an activated complex or a transition state. This is where your bonds would be breaking. So if you're thinking about the hydrogen and oxygen reaction, you would have to provide energy to break these bonds, while at the same time new bonds would be forming between hydrogen and oxygen. So up here, you're not a reactant or a product. You're in the transition state or you're an activated complex. This is a highly unstable and high energy arrangement of atoms. So again, here are your reactants. As they gain that energy and climb that energy barrier, you can see that they begin to rearrange themselves into something that's neither a reactant or a product. Now, if you don't have enough energy to make it over that barrier, you would simply fall back down to reactants and you would never see anything happen. The reaction simply would not occur. But if you can make it past that barrier, past that activated complex, then you'll start becoming products, and finally the reaction will go to either equilibrium or completion. The activation energy, okay, and the activated complex or the transition state, depending on how you want to refer to it.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
So at the transition state, you are at the highest energy level possible, okay, and the most unstable state possible.
Let's analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecules are in a transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.
So let's look at some factors that affect the rate of a reaction. First, you have temperature. Temperature changes. The higher the temperature, the faster the molecules are moving. The faster the molecules are moving, the greater the collision frequency will be. Also, you'll have more molecules that have that necessary energy. So at a higher temperature, you have faster moving molecules. This will give you more frequent and a higher energy collision. Okay. If you have more frequent collisions, okay, and higher energy collisions, you're going to have a faster rate. You also will have more molecules that have the necessary energy. So if this is the energy barrier right here, represented by this line, and this is the temperature 1, okay, and this is temperature 2, you can see that at temperature 1, the molecules underneath this area of the curve all have the necessary energy. Okay? At temperature 2, only these molecules in this area have the energy necessary to complete the reaction. So the higher the temperature, the more molecules have the necessary activation energy. Again, this is a Boltzmann's distribution. This would be the higher of the temperatures. Okay. The red line indicates the higher temperatures. Not sure why my ink keeps changing. There's the higher temperature, and there's the lower temperature. The molecules, this would be the average temperature of both reactions. Okay. If the activation energy necessary for this, or the energy barrier, is somewhere around here, you can see that more molecules at the high energy, the area under the curve, would have that energy at T2, or the higher temperature, than those at T1. So that's the energy barrier. Very few molecules have that necessary energy, period. Most of them have an average energy. Some of them have a lower energy. When you increase the temperature, you not only broaden that curve, but you increase the area under the curve that will give you a higher number of molecules with the necessary energy. Concentration. We know that increasing concentration also increases rate. Anytime we want a faster reaction, we know that we can increase the molarity of our acid, or for a gas, we would be able to decrease the volume of the container. But if the molecules are closer together, then they're going to collide more frequently. You're going to get a faster reaction. So 1 molar HCl versus 6 molar HCl, it's pretty clear that the 6 molar is going to react faster as you have more collisions that are closer together, because you literally have more molecules in contact with each other. Particle size can also affect rate, since collisions occur only at the surface. And to get a collision to be effective, we know we need enough energy and the right orientation. And now you've got to have only those at the surface that are going to collide. So if you have smaller particles with a bigger surface area, you're going to get more collisions. So again, to heat this solid up while it's in a pile doesn't give you nearly the explosive rate that it would if you blow this powder into the same amount of energy. You have dispersed, again, those particles and created a greater surface area, thereby a faster reaction, because you have a greater collision frequency. Anytime you can get more collisions, you're going to get a faster rate. Catalysts also change a reaction. They do that by a very different method. They change the mechanism. So yes, they do lower the activation energy. So if it normally takes this much energy for your reaction to occur, and you can decrease that amount of energy to just this amount, then your reaction is going to go faster. But the mechanism by which they do this is fairly complex. So it does give you a lower activation energy and a reaction that proceeds at a higher rate. You simply don't have to climb the same energy barrier if you have a lower activation energy. So when you look at a rate equation, you're really just looking at the change in concentration of a substance over the change in time. So concentration A at T2, concentration A at T1, divided by T2 minus T1. Again, just change in concentration over time. So let's look at a typical simple reaction that's simply a synthesis reaction between hydrogen and nitrogen gases to form ammonia gas. This would be a fairly fast reaction because a gas has a much faster rate of reaction since the particles are moving faster and certainly have greater collision frequency than a solid or a liquid. If we look at the reaction and we look at our concentration versus time, so we're going to look at concentration versus rate of time. If this is our hydrogen and it decreases at this rate, obviously hydrogen's a reactant, its rate is going to decrease. As we use up the hydrogen, there'll be less of it to collide, so it should make sense that over time the concentration decreases as it turns into the product. The nitrogen will decrease as well, but it's going to decrease at 1/3 the rate of hydrogen. There are 3 times stoichiometrically as many hydrogen molecules as there are nitrogen. Therefore, with a decreased concentration, you're going to have 1/3 the rate. The ammonia will increase, so it starts out at nothing and then increases. Okay? Its concentration is going to increase over time, and it increases at twice the rate of nitrogen, or 2/3 the rate of hydrogen. To calculate rates, we can take average rates over long intervals, or we can take instantaneous rates by looking at the slope of a tangent line. You know, maybe some of you know, that the slope of a tangent line is a derivative. This is your typical average slope method. You take 2 points on a line and you find the rise over run or the slope of the line. The instantaneous slope method will give you the actual rate at that particular time. A rate law, will not include the concentration of the products because the products have not formed to any large degree yet. So when we deal with a rate law, we're looking only at the concentrations of reactants. These rate laws must be determined experimentally. They cannot be obtained from a balanced equation. So a rate law is going to include only reactants, and they have to be determined experimentally. You cannot use a balanced equation. So the rate law for this equation would have this general format. Rate is equal to K. Brackets, again, mean molarity. And this order would have to be determined from an experiment. So this is a rate law expression. K is the rate constant. It's a lowercase k. N is the order of the reactant. It's usually a positive integer, and it must be determined experimentally. When you look at orders, so this would be a substance A that's a first order reaction. And a graph of that, rate versus concentration, gives us a straight line with y equal to x. And what this means in simplest terms is that if you have an order of 1 with respect to your substance, it means that when the concentration of A is doubled, then the rate is doubled. It's a first order relationship. If A was tripled, the rate would triple. Again, a first power or first order relationship. A second order relationship means that when A is doubled, this is sort of a square relationship, when the rate is doubled, when the concentration is doubled, the rate will quadruple. If the concentration was tripled, it's still a square effect. the rate will become 9 times greater. Second order. A second order, okay, with respect to your reaction, has a much larger effect on your rate than a first order. A third order reaction would mean that if, and again, that would be a cubing, means that when A is doubled, you would have a rate 8 times greater, 2 cubed. And when 8 is tripled, so you'd have a 3 cubed relationship, you have a 27 times greater rate. So what you're looking at is, and we don't know why yet, you have yet to learn why substance A might have a first or a second or a third order. Okay, that would have to do with structures and many, many factors. But obviously, if a substance is third order, then changing its concentration hugely affects the rate. So we'll stop here and pick up with rate laws as we move into the next sections of the chapter.